All right, so we're back talking about section 1.5, which are the quadratic applications, and which is the last big application that you'll see in this this chapter, this book uses, and that's the height of a projectile. So if you're following along in the note packets, we've come to this formula. S equals, so S is how high the object is as a function of time t, usually in seconds, measured in seconds. How many seconds after you throw something in the air, whether it's football, baseball, cannon, propelled, whatever object is being propelled into space, there's an initial velocity of how hard it's propelled. That's what we'll plug in for V, and it's time in seconds. And then plus there's an initial height, how high up off the ground was the object when it was propelled. So again, T will be after how many seconds. It goes up. You know, maybe after 1 second, it's this high, 2 seconds, 3 seconds, 4 seconds. Depending on how hard it was thrown, it might go up faster, 4 seconds. And then eventually it starts coming back downhill. So how high does it go? Well, that's going to depend. How hard was it thrown? And how high were you when you started that? Like if it was off of a higher location. So again, this is the height off of the ground. This is how hard it's thrown, or initial velocity. T is time in seconds. Well, the -16 you might be questioning, that has to do with the pull of gravity. That's factored into it in this formula. And then S is how high does it get? How high up is it after T seconds? All right, so let's look at an example. So let's find that in our problem. For example, oh, I think I know what I did. I remember it's on the next page. I have a cannonball example that we're going to follow through with. So on the next page, find that with me. You will see we have this kind of cliff top here scenario. So we're on a 100-foot cliff embankment here. And we've got this cannon firing, going up, coming back down. So a cannon is going to be a lot more velocity than this arm throwing I've been showing you, right? So it's going to be a big number, 600 feet per second in this problem. So it tells you the velocity of this cannon. It shoots it out at 600 feet per second. And we're on a cliff that's 100 foot tall. So we're going to fill in, and again, these are always given in your reading. Just look for that. The velocity will be in feet per second or something that sounds, you know, like that. It will probably tell you the velocity is, or initial how hard it's thrown. And then height will just be that number, 100 foot, 2 foot, or from the ground. From the ground would be just put in 0, which makes the problem a little easier. But there will be an initial height given. So we're going to go back to our cannon problem, and we're going to fill that in with these numbers. 600 for V times time, and the initial height was 100 foot off that cliff. So now back over where we were in the notes. We can do, like in the middle of the page, I plugged in 1 second. So we can answer questions like, well, how high is the cannonball after 1 second? How high did it get? Just 1 second in. It's pretty fast, right? -16 times 1 squared plus 600 times 1 plus 100. Plug that in your calculator, boom, right out. It will tell you, we can just do that all without algebra, and that comes out to be 684. So 684 foot from the ground is our answer. We could continue down this route, and that's what I want you to do on number 2. Now figure out how high the cannonball is at 2 seconds. All right, so take a minute, plug that in. And I'm getting 1236 for that. So 1236 foot after 2 seconds. So it's going up pretty quick, right? Then we could do 3 seconds, 4 seconds. And you exactly might be asking, exactly, isn't that graphing? And it is. That's what we're going to lead into in the next chapter. We'll be graphing. And that is a graph. Like this would be the X value. I know we're using T for time here, but it would be the X value, the X axis, the how long is the value this way, and then how high is the vertical answer that way. So where they intersect would make a point in space, and that's what's going to graph to make this neat curve that I'm talking about, this parabola. So this would be like the x value 3 if we were doing a t-table to find the graphing. Not to get too far ahead of ourselves, because we got plenty to worry about right now, but just if you want to know, it does connect into graphing later, and we'll come back to that at that point to see how we could just use our graphing calculator really to do a lot of this. But for now, just understanding the formula, we can put in different times and then calculate it and spit out y values. How high up is it? That's the s value. You know, in algebra, I should back up and say I'm calling x t and I'm calling s y and things. When we're doing a reading problem, a lot of times we get rid of the or away from the just dry x and y axis, and we use letters to mean more valuable things in this particular formula. But it really is still just an XY scenario. That's just the generic default letters we use. But we could think about this time as being what we'd normally put in as an X, just general X, and then this being the Y equals. But we're spicing it up with this formula using letters that kind of mean something in the particular situation we're talking about. But again, that will also come later in our discussion. But you've noticed, I'm sure, we've started using some different letters in the applications than just regular X and Y. All right, so let's check your work. Let's all do the 3 seconds just to get a feel for how this is going up in space. So it's negative 16 times 3 squared plus 600 times 3 plus 100. I'm getting 1756. And so a good question you might be asking is, when's this going to start coming back down? And that's a very good question. We are definitely going to talk a lot about that. At some point it won't go just infinitely. Gravity keeps pulling at it, so eventually it's going to come back down to the ground. It's going to turn around and start back down to the ground. And we could keep plugging in numbers and kind of watch for that to happen. But the harder thing for us to figure out, that you'll spend more time in your homework doing, because we do a lot of algebra, right? That's what we do, is the algebra to this would be, we'll figure out the time given the s value. Have to figure it out the other way. So let's say, back to our original problem, let's say we wanted to answer, when will it reach 700 feet above the ground? So we could ask, when will it be different heights? And we could put the height in here, 700 feet above the ground. And now that's going to take us more time. We're going to have to do our quadratic formula, quadratic equation stuff. So now it's a quadratic that we have to solve. So we want to get it all on one side equal to 0. And you might notice in your packet that I've done that. So I brought the 700 across. Minus 700 made minus 600. Got it in my standard form. And then divided through by, I divided through by -4 actually, and got it in a standard form. Divided through by -4 made it 4t squared. Oh, I can tell. I was doing the one on your packet. I did hitting the ground. I didn't show this one. So let me just show it to you. I could divide through by, let's see. I could at least half all those numbers. I think I can divide by 4. I think I would still stick with that. I would probably divide through by 4, maybe even -4, so my front number will be positive. Not that it has to be, but that would make that a positive 4t squared, a negative 150t, and 4 goes into 600, 150 times. And then I could use that as my ABC, plug that in my quadratic formula, or go through the factoring to get my 2 solutions. So there'll be 2 points in time that this cannonball goes up to 700 feet. So there could be 2 viable answers. I know in our other examples we had to throw out one of our answers a lot of times, but there could be really two viable answers, because the cannonball goes up, maybe hits 700 feet after not much time, and then it goes up higher, and then as it turns back around, there's another point in time where it comes back down to 700 feet before hitting the ground. So 2 viable answers is possible here. So let me do the example I have on your packet here where I did hitting the ground. That's a common question asking your homework is wants to know how long does it take this thing to get back down on the ground. You know, it's going to go up in space, up, 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 turn around. It'll eventually come back down and hit the ground because the gravity's pulling it. So when does something hit the ground? Well, that's an algebra question we can solve. It hits the ground when our height above the ground is 0. So we plug in this value as 0 anytime that's the question. Again, you should have the velocity given in the reading and the initial height, and then plug in how far it is above the ground if that's what's given. So hitting the ground means you're at 0. So 0. So this is our problem, the one that you see here. I have again divided that by -4 to get negative over negative is positive. 600 divided by -4 is -150. And 100 divided by -4 is -25. And that's the problem you see at the bottom of your page where I plugged that in as my A, B, C. I crunched it in the quadratic formula. And this time I couldn't have factored. These answers didn't come out to be nice rational solutions. So I did actually have to use the formula. And I got 2 solutions. A negative answer, which isn't usable in this case. Like I said earlier, sometimes you do have 2 viable answers, but negative will not work for us, negative time. So I won't be able to use that, but we do have 1 viable answer, and it's about 37, 38 seconds. It takes a little while to go. It's going to go up pretty far, actually, so my picture isn't quite hitting it. It's going to go quite a bit more because it's going to take a full almost 38 seconds before this cannonball comes back down to the ground, which actually isn't super long, right? It's still quick, but longer than maybe my picture would infer. And again, we can do this problem over and over in so many different ways. We can put in, when is it 20 feet above the ground? When is it 1,000 feet above the ground? 2,000? Does it get up to 3,000? I don't know. At this point, we won't stress you with that, but later on, we're going to figure out how high, what's the highest point that it gets to, which is going to be the vertex. So we'll be doing that in the next chapter, finding the vertex of this. We'll use our graphing calculators to help us with that too, but we can also do it algebraically. We can plug in any number right here, do this quadratic thing to it, and spit out the solutions. All right, lastly, the last part of it is called modeling. We saw modeling with linear equations. And we can have, it's actually some of the easier problems for you to work, although they might look intimidating because they're wordy, but the work is kind of done for you if we're modeling. Again, modeling means someone has crunched the statistics and studied a scenario and come up with an equation that defines it. So they've done kind of the reading problem stuff for us and said, okay, here's an equation. Your job is just to read it carefully and see what X and Y represent. So take a minute and read that again. Feel free to pause the video. And the one I'm doing here talks about the salary in millions of dollars for rookies selected in the first round of the NFL. This was a 2014 data. Draft can be approximated by this quadratic model. So we can plug in the year, or not the year, but the draft pick. If they were first draft picked, we plug in 1, second draft pick 2, so on and so forth. And it'll tell us how much money they made in millions. So the example I have here, I plugged in the first one selected. And if this be true, and I believe it is a true data points example from Real Stats, if you plug in the first draft pick in the year 2014, you might Google it and check me, but if you plug that in as 1, that's arithmetic. It'll spit out the answer, and here you can see in my example, it gave me 22.0258, or about $22 million. First draft pick. So we could keep on doing this on the next page. I show you I plug in 7, and we could do that all day long, just like with the projectile example we did. You can plug in for T a lot easier than the second kind of question is, well, what if, this is the last note, what if you wanted to know which player got $11 million? You would plug in over here instead. If you had to do it the other way, here's a modeling equation, and you wanted to know $11 million. When does that happen? Then we would be in our algebra world where we have to solve the quadratic equation. We'd throw that across the line, get it equal to 0, solve our quadratic equation with the formula or by factoring. And we know those can kind of be tedious problems. So that's the harder work we do, but that's what we're doing on 1.5. So let me know if I can help with that, and best wishes to you.